Thousands of vibrations per second force the air to tremble, creating bass lines that physically shake the body. A single wave turns a small room into a zone of high acoustic pressure. One can notice how the cone pulses, displacing the atmosphere. But this is just the beginning. At first glance, the shell looks like a simple sound device, but in reality, it is a machine that controls the air itself. Why use copper coils thinner than a strand of hair? The heavy outer casing hides these delicate elements. They allow the mechanism to convert electricity into precise motion instantly. Sheets of metal unite with the windings in a structure assembled with absolute precision. It is visible how the device transforms silence into an acoustic explosion in a matter of seconds. Engineering merges with physics to turn current into resonance. Transition to the next level. The sound wave begins its physical propagation. 150,000 units leave the assembly lines every single day. Factories operate around the clock, producing enough devices to fill a city with sound in just 24 hours. The global market generates nearly $11 billion annually. But this is just the beginning. Technology giants invest hundreds of millions of dollars to refine the listening experience. Why is the physics of sound so critical? It seems simple to play a melody, but in reality, a speaker does not create sound the way we imagine. Every rhythm is nothing more than air in motion at a microscopic scale, engineered to evoke energy. One can notice how invisible vibrations permeate the spaces where we live and work. Thus, the electrical signal transforms into acoustic reality without haste. Two main types of magnets dominate the global speaker manufacturing industry today. Engineers choose carefully based on the desired audio performance and the specific size of the driver the magnet powers. Ferrite is chosen for being heavy, affordable, and remarkably durable, while neodymium is prized for its lightweight nature, exceptional strength, and significantly higher cost. At first glance, they seem like simple metal components, but in reality, their composition defines the precision of every sound emitted. But this is just the beginning of their formation. The creation process initiates within the blazing heat of industrial furnaces. It is visible how a precise mixture of minerals and rare earth metals melts at temperatures exceeding 1,000 degrees Fahrenheit. Why is the molten material compressed immediately after pouring? Ideally, the liquid metal would simply cool in the shape of the mold without intervention. This pressure is necessary to form dense magnetic blanks, typically in cylindrical or ring shapes, depending on the specific speaker design. Transition to the next level. One can notice how the blanks enter shielded chambers designed to prevent external magnetic interference. High-power systems discharge immense electrical pulses, so powerful they could pull nearby steel tools right off a workbench. This sudden magnetic surge forces the internal magnetic domains of the material to align perfectly. The once inert metal block transforms into a permanent magnet with strong, stable, and long-lasting magnetic fields. It gets more complex further on. Such extreme heat used earlier serves to stabilize the magnetic structure effectively. This ensures durability and essential resistance to demagnetization over time. Therefore, once cooled, each blank is transferred to precision machining stations. It is visible how the equipment mills the material into its final cylindrical or ring form. The component achieves the exact dimensions required for speaker assembly, ready for installation. A miniature motor capable of converting electrical signals into precise mechanical motion enters the vibration mechanism beneath the magnet assembly. The copper voice coil utilizes pure copper wire coated with ultra-thin insulation. This ensures optimal conductivity without the risk of short-circuiting. One can notice the fine wire feeding into the system for processing. Why does copper remain an almost irreplaceable choice in audio engineering? At first glance, The material choice seems standard for electronics. However, copper is essential to form the sophisticated muscle bundle at the heart of the moving system. High-precision, automatic winding machines form the cylindrical coil around a core or bobbin. It seems like a simple rotation, but in reality, the system strictly controls tension, speed, and direction. Each turn must sit in the exact position to generate a stable and uniform electromagnetic field. But the process is only gaining momentum. One can see how the layers stack together depending on the loudspeaker type. Finally, the entire coil is coated with heat-resistant adhesive to secure and protect it. This bonding layer ensures the component withstands the stress of operation. Electrical energy transforms into motion here, allowing the voice coil to fulfill its purpose without haste. One specific component acts as the amplifying arm that transforms simple mechanical motion into audible sound. If the voice coil serves as the engine, the diaphragm stands at the very center of the acoustic signature. Why is the selection of materials for this diaphragm so critical? At first glance, the shape seems to be the primary factor defining the acoustic profile, but in reality, the material itself determines responsiveness, necessitating light and resilient options like polypropylene, fiberglass, pressed paper, or mylar. In high-end loudspeakers, titanium or carbon fiber may be chosen to enhance responsiveness without introducing distortion. Sheets of these diverse materials are cut into circular blanks to prepare for the thermal forming stage. Inside the press, metal molds with fixed geometry heat and compress the material at high temperatures. One can notice how the flat blanks gradually take on the characteristic cone or dome profile under the immense force. But this is just the beginning. Strict control over pressure, temperature, and pressing duration is mandatory for every material type to prevent warping or edge tearing. It seems like a standard molding process, but in reality, details such as rib patterns, depth, and cone angle are carefully engineered to ensure proper frequency response. Even a millimeter of deviation can influence the final acoustic performance. Some diaphragms undergo surface treatment to increase durability or receive protective coatings against moisture and static charge. It gets more complex further on. To verify absolute uniformity, technicians employ advanced optical verification methods. Laser scanning systems map the diaphragm surface, comparing it to the original design blueprint. Through this balance of optimized materials and tightly controlled geometry, each diaphragm leaves the factory with near-perfect consistency. The component is now ready to take its place in the assembly. 0.1 millimeters is the absolute maximum margin of error allowed during the critical integration phase of the magnetic assembly. From separate heavy components, including the magnet, the pole ring, and the top plate, technicians build a unified magnetic module where every part must be aligned with absolute accuracy. The magnet is placed first, followed immediately by the pole ring and the top plate, which are pressed firmly into position using a specialized alignment machine. At first glance, this stacking looks straightforward, but in reality, sensors embedded in the system continuously monitor for microscopic deviations and adjust automatically to create the correct magnetic gap for the voice coil to operate. Why is the mechanical centering collar installed before the adhesive even cures? Ideally, the magnets would hold themselves, but magnetic force alone is not enough for dynamic stability. The collar secures the axis of motion, effectively preventing the assembly from rotating or shifting during future high-volume operation. An automated dispenser moves in a closed circular pattern, applying glue to the bonding surfaces with calculated precision. One can notice how the adhesive spreads evenly into the guide grooves without foaming or overflowing the edges. Algorithms control the pump pressure, flow rate, and volume to ensure the concentricity of the magnetic assembly remains undisturbed. But this is just the beginning. Only a few seconds later, the adhesive begins to cure, creating the initial bond that locks the module into a single solid structure. The spider is then bonded onto the frame, ensuring the voice coil moves strictly along one axis without lateral drift or twisting under high-frequency oscillation. Once the spider adhesive has fully set, the magnetic mechanical assembly is unified, completing a fully formed driver core. If a loudspeaker were an electronic instrument, the coil would serve as the source of motion, while the diaphragm becomes the surface that delivers sound. These two elements cannot function effectively without each other. The process begins with the coil being placed into the narrow magnetic gap between the magnet and the pole core. A deviation of only fractions of a millimeter here can disastrously alter frequency response and sensitivity. Depending on the specific speaker design, the coil is mounted either by hand or by automated pick-and-place systems. It gets more complex further on. Leads are soldered to electrical terminals for connection, creating the necessary electrical pathway for the signal. At the same time, the diaphragm, made from compressed paper, polymers, or carbon fiber, is positioned and bonded directly to the coil using specialized adhesive. One can see the technician applying the compound, a stage requiring both mechanical precision and skilled craftsmanship. Even slight misalignment can cause coil rub and distortion, so clarity and accuracy are truly shaped here. Once the voice coil and diaphragm have been securely bonded, the assembly is immediately placed into a specialized curing chamber. The duration ranges from 20 minutes to several hours, allowing the heat-resistant adhesive to fully harden. This locks every component in place, forming a stable mechanical structure while preserving the diaphragm's natural flexibility. Finally, technicians perform a manual inspection using directed light, ensuring the diaphragm and coil are fixed exactly as designed with no contact against the magnet. The driver is now ready for the next phase of assembly. .1 millimeters is often the maximum allowable tolerance for cutting the wood panels using high-speed computer numerical control machinery. With the driver components now complete, the production line transitions to cabinet construction, a stage that fundamentally determines the loudspeaker's overall acoustic performance. Engineers favor materials like medium-density fiberboard or birch plywood for their exceptional structural stability and acoustic neutrality. The automated blades slice through the wood with immense precision, ensuring every cut matches the original blueprint. This is critical because even a deviation of a few millimeters creates air leakage, which would weaken bass response and reduce system stability. The process is only gaining momentum as the panels move to the assembly station. Why do technicians use both industrial adhesives and mechanical fasteners during assembly? At first glance, using heavy-duty glue might seem sufficient to hold the wooden box together. But in reality, this dual approach ensures the cabinet can withstand continuous vibration at high playback levels without developing mechanical failures. The adhesive chemically bonds the surfaces to create a seamless seal, while screws reinforce the structural rigidity. Inside the enclosure, structural braces are strategically placed at high resonance points to stiffen the frame against the energy of the drivers. At first glance, the interior looks like a simple void, but in reality, it is a complex acoustic environment. Technicians manually install damping materials such as acoustic foam or dense mineral wool to line the internal walls. One can notice how the fibrous texture is pressed into corners to absorb sound energy and reduce internal standing waves. These elements suppress unwanted resonance, resulting in a cleaner output. But this is just the beginning of the tuning process. Technicians then machine precise openings for the woofer, tweeter, and bass reflex port. Each position is calculated according to the crossover frequency and internal airflow behavior to allow every driver to perform at full potential. Once the wooden body is structurally complete, the exterior is finished with vinyl wrap, lacquer, or acoustic fabric. This layer protects the enclosure from moisture, enhances appearance, and subtly shapes surface reflection characteristics during playback. The loudspeaker cabinet only becomes a true audio instrument once it enters the final manual assembly stage. Here, each acoustic element is installed by hand, following a carefully structured sequence to guarantee consistency. Technicians route signal wires through narrow internal channels to connect the crossover board and rear terminals. It is visible how the cable positioning is adjusted to avoid electromagnetic interference. The wires are secured tightly, so they never obstruct the airflow within the enclosure during heavy bass excursions. Everything only gets more complicated as the main components arrive. The drivers, woofers, and tweeters are seated into their designated mounts with extreme care. Every screw is tightened to a specifically calibrated torque to ensure mechanical stability without damaging the chassis. Too much force risks deforming the frame, while too little can cause vibration or mechanical noise. Once the wiring is connected, the cabinet undergoes a rigorous structural inspection where panel air tightness and port alignment are verified one by one. The loudspeaker then moves into the critical testing phase, where selected samples are placed inside a soundproof anechoic chamber. Sensitive microphones measure the full frequency response from 20 Hz to 20 kHz. Comparing the result to a strict reference curve, one can notice the silence of the room before the test tones begin their sweep. Transition to the next level. Some models are driven at high volume for hours to simulate real-world stress. Only after passing all stages is the speaker thoroughly cleaned and prepared for packaging. It is placed into a custom-shaped cradle and cushioned with thick shock-absorbing foam to prevent impact damage. Multi-layer cartons are sealed and arranged onto pallets, ready to leave the factory and play the first notes. Zero technical flaws are tolerated. Every professional loudspeaker is a result of precision engineering and uncompromising quality control. One can notice how verification covers everything from the smallest components to the final stage of testing. But this is just the beginning. Why is such strictness required? At first glance, it is just a device that produces sound, but in reality, it is a verified acoustic structure. It gets more complex further on. The system is designed to deliver emotion in its purest form to the listener. Engineers ensure the physics work correctly. It is visible how the unit performs. Thus, the instrument is ready for operation,